Hello everyone. In this video, we are discussing about the deadlocks in operating system. It is the overview that we learn resources, then we learn why do deadlock occur and dealing with deadlocks like ignoring them, detecting and recovering from deadlock, avoiding deadlock, preventing deadlock. So resources, something a process usually limited at least somewhat. Example of computer resources like printers, semaphores, locks, table in a database. Process need access to resource in a responsible order. There are two type of resources. First is printable resources. It can be taken away from a process with no ill effect, and non-printable resources are will cause the process to fail it taken away. So when do deadlock happen? Suppose process 1 hold resource A and request to resource B, where process 2 hold and B requests A, where both can be blocked with neither able to proceed. Deadlock occur when processes are guaranteed exclusive access to devices or software constructs resources. Each deadlock process need a resources held by another deadlock process. Here it is using resources, sequence of events required to use a resources, request the resources, use the resources and release the resources. Cannot use the resources if request is denied. Requesting processes has options like block and wait resource, continue if possible without it, may be able to use an alternate resources. Third is process fails with error code. Something of this may be able to prevent deadlock. What is deadlock in operating system? A formal definition of deadlock is a set of processes is deadlocked if each process in this set is waiting for an event that only another process in this set can cause. Usually, the event is releases of a currently held resources. In deadlock, none of the process can run, release resources and be awakened. These are the four conditions for deadlock. First is mutual exclusion. In this, each process is assigned to at most one process. Second condition is hold and wait. In this, a process holding resources can request more resources. And third is no preemptions. Previously guaranteed resources cannot be forbiddenly taken away. In circular wait condition, there must be a circular chain of two or more processes where each is waiting for resources held by the next member of the chain. Next is resource allocation graph. Resource allocation modeled by directed graph. For example, in example 1, resources are assigned to A. Resources are assigned to A. In example 2, process B is requesting for resources S. In example 3, process C hold T waiting for U, and another process holds U waiting for T. In third, C and D are in deadlock. It is the graph for multiple resources. Reallocation graph for multiple resources. It is a graph with a cycle but not on dead but no deadlock. Here is in basic facts. If graph contain no cycles, no deadlock occur. But if graph contain a cycle, if only one instance per resource type, then deadlock. Necessary and sufficient conditions. If several instances per resources type, possibility of deadlock, necessary conditions. How to deal with deadlocks? How can OS deal with deadlock? First, ignore the problem altogether. Hopefully it will never happen. Second, detect deadlock and recover from it. Third is dynamically avoid deadlock. Carefully resource allocation. Fourth is prevent deadlock. Remove at least one of the four necessary conditions. We will explore this trade-offs. Getting into deadlock. Not getting into deadlock. Many situations may result in deadlock but do not have to. In previous example, A could release R before C requests R, resulting in no deadlock. Can we always get out of it this way? Find ways to detect deadlock and reverse it. Stop it from happening in the first place. This is the ostrich algorithm. It pretends no problem reasonable if deadlock occur very rarely. Cost of preventions is high. In Unix and Windows, take this approach. Resources like memory, CPU, disk space are plentiful and deadlocks over such resources rarely occur. Deadlocks typically handled by rebooting. Trade-off between convenience and correctness. This is how we detect deadlock using graphs. Process holdings and requests in the table and in the graph, they are equivalent. Graph contains a cycle, then it has deadlock. Easy to pick out by looking at it. In this case, need to mechanically detect deadlock. Third is not all processes are deadlocked. A, C, F not in deadlock. Here now we see how deadlock detect. These are the deadlock detecting algorithms. General idea, try to find cycles in the resources allocation graph. Algorithm, depth first search at each node. Mark arcs as they are traversed. Second, build list of visited nodes. Third, if nodes to be added is already on the list, a cycle exists. Where cycle is equals to deadlock. For each node n in the graph, set L is equals to empty list. Unmark all arcs traverse NL. If no deadlock reported by now, there is not any. Define traverse CL. In this, if C in L report deadlock, add C to L. Now for each marked arc from C, where mark the arc, set A is equals to arc destination. Note, L is a local variable. Traverse AL. This is the resources with multiple instances. Previous algorithm only work if there one instance of each resource. If there are multiple instances of each resource, we need a different method. First, track current usage and request for each processes. To detect deadlock, try to find a scenario where all processes can finish. If no such scenarios exist, we have deadlock. Detection algorithm uses. When and how often to invoke depends on. First is to how often a deadlock is likely to occur, how many processes will need to be rolled back, one for each disjoint cycle. If detection algorithm is invoked arbitrarily, there may be many cycles in the resources graph, and so we would not be able to tell which of the many deadlock processes caused the deadlock. This is how recovering from deadlock options like recovery through resource preemption, recovery through rollback, recovery through killing processes. In the recovery through resources preemption, how it works? Take a resource from some other process, depend on nature of resources and the processes. Next is recovery through rollback. Check point in this. First, it check a point process periodically. Second, use this saved state to restart the process if it is not found deadlock. Third, may present a problem if the process affect lots of external things. How it recover through killing processes? Crudest but simplest way to break a deadlock: kill one of the process in the deadlock cycle. Other process can get its resources. Preferably choose a process that can be rerun from the beginning. Pick on that has not run too far already. Deadlock recovery process termination. Abort all deadlocks processes. Abort one process at a time until the deadlock cycle is eliminated. In which order should we choose to abort? First, priority of process. How long process has computed and how much longer to completion. Third, resources. The process has used resources process need to complete. How many processes will need to be terminated? Is process interactive for batch? This is how preventing deadlock. Deadlock can be completely prevented. Ensure that at least one of the conditions for deadlock never occur. Mutual exclusion. Circular wait, hold and wait, no preemption, not always possible. Eliminating mutual exclusion. Some devices such as printer can be spooled. Only the printer daemons uses printer resources. This eliminates the deadlock for printer. Not all devices can be spooled. Principle is to avoid assigning resources when not absolutely necessary. As few resources as possible actually claim the resource. Attacking hold and wait, requiring process to request resources before starting. A process never has to wait for what it needs. Second thing is this can present problems. A process may not require resources at start of run. This also ties up resources other processes could be using. Processes will tend to be constructive and request resources they might need. Variations. A process must give up all resources before making a new request. First is to process is then guaranteed all prior resources as well as the new one. Problem is, what if someone grabs the resources in the maintain time? How can the process save its state? Attacking no preemptions. This is not usually a visible option considered a process given the printer halfway through its job. Take away the printer confusions issues. May work for some resources. Verbally take away memory pages, suspending the processes. Process may be able to resume with no ill effects. Attacking circular weight, assigning an order to resources. Always acquire resources in numerical order. Need to acquire them all at once. In circular weight is premeditated. A process holding resources n cannot wait for resources m if m is less than n. No wait to complete a cycle. Place resources processes above the highest resource they hold and below any they are requesting. All arrows point up. Deadlock prevention summary, mutual exclusion, pause, spool everything, hold and wait. It requests all resources initially, no preemption, take resources away, and circular wait, order resources numerically.